Lorentz transformations and look at what the implication is, you'll find, and again, length here, L is just the length, it's the distance between the two ends of your curve. What you will find is this result. Okay, that's the easiest way to plug it in and get this relationship. L prime equals gamma times L. I'm going to immediately invert this and write that L, this remember is the length measured in the stationary reference frame, where this thing is moving by you at a certain speed. Well, it's related to the length observed for, if you're looking at measuring something in that moving reference frame, that's L prime, then it's related by this, okay? Now remember that gamma is always greater than or equal to 1. And so this thing on the left-hand side is always smaller than this thing, okay? So this means that you, observing something moving by you at a certain speed, the person in that reference frame measures a certain length, whatever the length is in their own reference frame. What you will observe as that thing passes by you is a length which appears shortened or lesser as it moves by. So this is the length contraction. And again, remember, you are observing this as something moves by you. That's the length measured in the moving reference frame, but measured by that person. And then this is the length you observe in the, let's say, stationary observer frame as it goes by. Okay, I'm looking for hands or expressions of disdain or something. Yes?
The stationary reference frame can also be moving, right?
Yeah, absolutely. So a lot of the natural tendency, which gives rise to interesting questions right off the bat, when you're presented with either time dilation or length contraction, is of course you're tempted to say, well, what about if I switch reference frames and look at it from the other person's perspective? It's exactly symmetrical. The same phenomenon appears, and the same phenomenon exists. And this is where what are often called paradoxes shows up, okay? Because if it's totally symmetric, you might say, well, okay, the length of an object, something moving by, to me, appears shorter, but if I turn things around and I'm the person in the moving reference frame and I look at me, well, from their perspective, I'm moving with the same magnitude velocity, but in the other direction. And am I going to see the exact same effect? And the answer is yes. And so the question is, how do you reconcile those two observation vantage points where both people observe time to be dilated in the moving reference frame, or both people observe length could be contracted in the moving reference frame? How do you reconcile them? And that's always the kind of tricky part of this. I don't find our textbook to be very good on the reconciling of these things. I think the green resource that I suggested to you is a better one. The Space-Time textbook is a really good one, but it's a big book, so you probably don't want to work through that. I haven't had a chance to get far into the video thing that Luis forwarded to me, but it looks like it's going to be pretty good as well. So again, you need to think about this and try and figure out how lengths and times measured in the different reference frames feed together, and then how you can reconcile this apparent paradox that it's an entirely symmetrical vantage point. And I don't know how to do this in an easy way other than to kind of just sit down and work through it.
So returning to time dilation, when you say that if you're like watching a clock fly by, the clock will be going slower, that means that the time that you experience in the inertial reference frame is going to be longer than in the reference frame that's moving.
Correct. The time that you measure, yes. Yes. And we had some interesting discussions in office hour yesterday about, is this actually a real thing, in particular in the context of things like biological processes. It is a real thing. As I mentioned to some of you in office hours yesterday, even as early as the 1960s, I think it was, when we first had atomic clocks, these effects were measured and shown to be exactly in agreement with special relativity, simply by flying clocks around in aeroplanes at not so crazy speeds, a few hundred miles per hour. And it does talk about this in our textbook. So these effects are real, they're measurable, and yes, they would carry over into how quickly cells age or not. Yes?
So the names Lorentz Lorentz contraction and time dilation refer to the stationary observer as something is moving by?
Yes.
Okay.
So again, what I find I have to do always when I do special relativity problems, and it's like, I mean, it's so fascinating, but at the same time, it's super frustrating because you have to be meticulous about which reference frames you're referring to. And I find myself always asking and then adding a phrase in which reference frame, in this reference frame. And I kind of feel I have to do that all the time. So yes, to answer your question, the observations of time dilation and length contraction are what the stationary observer measures when she or he tries to determine the time elapsed or the length of something that is moving by them. It's what they perceive when they measure the moving object. Okay. All right. So, what is this? Oh, okay, yeah. This is the silly cartoon. Okay, I'm just going to let this run. So, this is what we see. Okay? So, this is what we perceive for something moving by us at certain speeds. 10% speed of light, no dramatic effect. But as soon as you get to appreciably high fractions of the speed of light, this length contraction is very dramatic. And objects appear to be pancaked into things that are very thin in the direction of relative motion. Okay? So that's basically, and keep in mind this is only in the direction of relative motion. The other coordinates, the other lengths stay unchanged. So this is a real thing, as I keep trying to emphasize. This is a slightly abstract context in which we actually see this in a field of research. That's something that goes on here at Columbia. You'll remember on Tuesday, I showed you very briefly the context in where time dilation is relevant in current research, and that was in cosmic ray studies, still an area of great interest. And I showed you in a fraction of a second the site of a very large cosmic ray observatory in Argentina. So, in fact, another place where special relativity becomes important in research that goes on here in this department and many other places is what happens when we take, for example, atomic nuclei and put them in particle accelerators, particle colliders, and smash them together. This is a field of research called these days relativistic heavy ion physics. And this is supposed to be a sort of cartoonish representation of two gold atoms, gold nuclei, sorry to be more precise, so they've been stripped of all of their electrons. Two gold nuclei that have been accelerated in different directions, and they're about to be made to collide together in the center of this screen. But from the vantage point of somebody who's in, let me say, a laboratory reference frame, having these particles come at high speeds from left and right, instead of looking roughly spherical, which is what you would expect for an atomic nucleus, they look like very much laterally compressed pancakes. And so these effects are very kind of significant when we do these types of research. It turns out, this is exactly what happens. Just as a footnote, why do we do this? It turns out if you take nuclear matter and compress it to high densities and high temperatures, it will behave in a rather surprising way. It kind of forms this sort of plasma, very hot, dense plasma of deconfined things called quarks and gluons. That's been an area of research which Columbia's been involved in for about 20 years. And not only does it have some surprising characteristics in its own right, it turns out this state of matter, so-called quark-gluon plasma, was presumably, as best we can tell, a state of matter that our universe was in about 10 to the minus 5 seconds after its creation. Okay? So if we can understand this in a lab setting, we presumably learn something about very early universe physics along the way. So that's why people have been very interested in this type of research. All right, so it's real. Length contraction is real. Time dilation is real. We've seen plenty of confirmations of it. The last thing I'm going to throw up on here, I am not going to worry about testing you on because it's already starting to push what I think is a first contact comfort level with special relativity. And we've talked about transformations in spatial measurements, length, talked about transformations in time, and of course the natural thing to do would be to combine them together and see what that results in terms of transformations of velocities, and that's all that this is, okay? So it's simply saying that if I was to figure out how velocities measured transform between two different reference frames, I should be able to figure it out by simply combining the expressions for delta x and delta t, and then just working through the algebra. And that's all it is, okay? And so this is essentially what drops out. Again, I'm not going to dwell on this too much. I don't want you to be grappling with a sort of second level two transformations at one time, when it's still going to take a little bit of time to become familiar with transformations individually in both x and t. But this is the way that velocity measurements will transform between two moving velocity, different velocity reference frames. Okay? So I'm going to count this as an FYI. So the velocity of anything moving in your reference frame. So up until now, we've kind of been imagining we're measuring sort of events. But if there's something that's, let's say, moving with a certain speed in my reference frame, I'm a stationary observer, and I want to know what velocity is measured by somebody who's in another reference frame, which is moving at yet another relative velocity, what is the velocity of that object that is, I started out describing in my reference frame? What is the velocity of that object as measured by the person in the moving reference frame? So I know that was a bit of a mouthful. So you can see why cartoons and drawings are so useful in special relativity. Saying things in words, if you're eloquent, will get you so far. I'm not very eloquent. So cartoons, I think, generally are very nice for kind of making sure that you're focusing on which particular things in these systems. All right, so let me say this is FYI. This is kind of where I want you to draw a line, okay? Up until this point, it's stuff I'd like you to know and be able to do some simple problems on. From this point on, it's all FYI, so you can, to some extent, relax, all right? So, space-time. We've still largely been treating space and time somewhat as distinct things up until now. But as you know, one of the very sort of useful things about special relativity is it describes a framework in which space and time can be put on a more equivalent kind of footing. And so the obvious question is, what does that mean and how do you do it? Well, to be put on a sort of similar footing, first thing you probably would want to do is that you would want to make sure these things have the same units or the same dimension. And an easy way to do that would be to take a time and multiply it by a speed, okay? So if I take something with time dimensions and multiply it by a speed, I'm going to get something which has length dimensions. And so there's an easy way to get time now represented with a length dimension. How do we do it? Well, I said you need to multiply it by a speed, and in special relativity, no big surprise, the speed that you're going to worry about is the speed of light, okay? So one of the early tricks that is used in sort of exploring relativity in more depth and then sort of describing it in a more compact, powerful way is to do just that. So we're going to take time and kind of fold it in using this sleight of hand by multiplying it by the speed of light to get something which we, I don't even know what to call it. Anyway, it's a quantity, okay? All right, so just c times the time of some event, let's say. So by doing this, you can sort of see that you're conflating space and time, albeit in a rather contrived way. And this is really what space-time becomes defined as, essentially. It's a four-dimensional space-time, where the time information is encoded in sort of spatial dimensions simply by multiplying it by the speed of light, okay? So if we do this, whereas we might be used to defining this as a 3-vector with coordinates in x, y, and z, we can extend this to become a 4-vector, and you'll hear about 4 vectors everywhere in special relativity. This is the first example. There's another one I'll mention before we wrap up. So now we've got a 4-vector notation something like this. Some quantity, x, because it's kind of spatial primarily, x to some coefficient here, which has indices which run 0, 1, 2, 3, okay? So it's just some construct, some maybe mathematical convenience at this point. But this is our first construct of a space-time 4-vector. All right, so why is this useful? Well, you've heard me say a couple of times on Tuesday that things that are invariant turn out to be kind of pretty powerful ideas in special relativity. And anything is invariant if it has the same value in, let's say, different inertial coordinate systems. So if we can identify invariance, in some sense that might give us an insight into physical behavior. And I would say this is a very prevalent theme in physics generally, looking for invariance and symmetries and things which change or don't change under the influence of changing some particular physical parameter. It turns out to give us a lot of insight. So I know it's a little bit abstract, but let me come back to the example that I showed you with a rotational transformation when we first introduced possible transformations between two coordinate systems. So here's an obvious example of something that is invariant or stays the same under a transformation, and in this case under a rotational transformation. So here's going back to my O reference frame, X, Y, and Z, and then I've got an O prime reference frame, X prime, Y prime, Z's are coincident, and they're still in the same direction. And what you saw briefly a few moments ago was that I could easily represent this by a simple rotation matrix if this is rotating by an angle phi in the XY plane. So there it is. Now, what might be invariant in this case? Well, what might be invariant, one thing for sure, is if I was to ask you how far away, again, for some reason I lost my red dot on the slide, how far away my red dot is from the origin, okay? So let's call that distance r, there it is. And if you look at this and calculated it in either of these reference frames, one of which is rotated with respect to the other, what you'll find is that the value you get for the square of the distance, and this is just a three-dimensional extension of Pythagoras essentially, you'll find that you get the same quantity, okay? So the distance from the origin in these two reference frames, which have been, there's been some transformation, in this case a rotation with respect to each other, this distance, of course, is the same. So this is an invariant quantity under this transformation. A simple example, but I just want to give you a sense of what we're talking about here. So, there's one example of an invariant. Let's see what we can do with this for 4 vectors, and in particular our space-time 4-vector. And it turns out that you can use these 4 vectors and create invariants which are, in fact, unchanging under the transformations of the boost transformations, the Lorentz transformations. And the thing that turns out to be invariant under those boosts is this quantity. So it's taking my 4-vector, and it's not, unlike on the previous slide where I did x squared plus y squared plus z squared using Pythagoras, it's a sort of modification on that. And it's taking the time component, squaring that, and then subtracting all of the 3 spatial components, okay? So it's creating a defined quantity, which is the time component squared minus each of the spatial components squared. So here's in a non-primed reference frame, time component squared minus x minus y minus z, or x1, 2, and 3 in this notation. It turns out that the same quantity measured in now my boosted reference frames moving at a constant relative velocity. It turns out it's the same quantity, okay? So here's a more abstract idea of something that's invariant. It turns out this is always invariant under these Lorentz transformations, and it turns out to be kind of a useful thing to work with. So, let's see, a bit of jargon. I think this is mentioned in our textbook, but if we define this quantity, as I just did on the previous slide, I already told you it has the same value in any inertial reference frame. And this is actually, in jargon terms, it's called the proper length of an object, okay? I don't care if this stays in your mind or not, but if you're going on to do more physics or you're interested in relativity, you'll often hear the phrase proper length. It's simply this quantity defined in the way that we talked about, okay? I'm certainly not going to talk about the stuff further down. That's just jargon. It's totally not of interest. But keep in mind that this 4-vector, the definition of it that I just described, is an interesting invariant for motions. All right. So now that we've defined it, we can, of course, if you think about it, that quantity could be either positive, or it could be negative, or it could be zero. Those are the three possibilities for it. If the quantity is greater than zero, if you think about the definition of it, it was the first component, which is time-like, even though it's multiplied by the speed of light to become a length. So if this is positive, it means the time component dominates the three spatial components, because I've got the time component squared minus the three spatial components squared. So if it's positive, this thing is called time-like, because the time component somehow dominates that 4-vector scalar product that I just defined. By contrast, if it's negative, it means some aspect of the three spatial components dominate over the time component. So it's called a space-like quantity. And it turns out, if it's zero, and you might think about this, or maybe we'll illustrate it in a few minutes, it's called light-like or null, because as with light and particles of light, this is a little bit of a throw-in from left field, the time and space components of this thing cancel out. Okay? So we can imagine these invariant quantities as being time-like, space-like, or light-like. And again, you'll hear those phrases perhaps quite a bit if you're going on to do more physics. All right. Now, you might recall on Tuesday, right at the start of class, I showed you a couple of cartoons of how we imagine time in a Galilean world, slices in space with time intervals, pancakes, if you will, stacked on top of each other. And then the slightly more cryptic thing that I showed you by analogy for special relativity, which is a series of little things that look like this. And so now is maybe a time to talk a little bit more about what these things actually represent. So let me just remind you for what you saw on Tuesday. We had a two-dimensional representation of truly a three-dimensional space in general. We're not showing Z because it's hard to represent 4 dimensions. So 2 dimensions along here and time running from bottom to top. Now, you could imagine that I have at this point in x, y, and this point in time, a certain thing happening, an event in the jargon of special relativity. As I go backwards, that's into the past, obviously. If I go forwards, it's into the future. And you can draw lines in distance versus time, or time versus distance, maybe more correctly, and kind of map out regions connected or possibly connected, related to this event, depending on how those lines look and where you fall within the lines. That was not very well explained, so let me try it again. All right, so all points are connected to this event, E, by lines moving at the speed of light, or representing motion at the speed of light. And so that's what these things are supposed to represent. And it's a 2D cone here, if you think about it. It's just rotated through 360 degrees. All right, so if you looked inside one of these cones, so inside this red cone in the future, or inside this blue cone in the past, all points inside these cones are time-like separated from this event here. You can start to see if you can reconcile this with the definition of that a squared or delta s squared vector. Outside of these cones, so in the regions that are not colored, then points out here are related to this by a so-called space-like separation. Okay? Now, an interesting thing to think about, and again, this requires, I would suggest, some thought, is anything that is outside one of these light cones cannot be causally related to this. okay? So that means those two events cannot cause each other. So they cannot be related to each other by causality. By contrast, anything that is within the light cone related to an event can have been, if it's in the future, it can have been affected by this thing, or it can have been, this can affect the thing up here, or if you look backwards in time, this could have been affected by whatever happened by another event inside the light cone. So this is the idea of a light cone and space light and time light and light separated events, if you will. So that also is something that becomes quite interesting, particularly this idea of causality and which things can or cannot affect other events. If you think about this, all it's telling you it's basically imposing the speed limit imposed by the finite speed of light. So, yeah.
Are things inside the cone also separated from V by space, just by time?
It can be both, but it's just a question of which dominates in that definition of the four vector. So that's all that it's telling you, which one dominates, if you will.
So points above and below E, but outside of the cone, are not separated by time?
They're not causally connected. So I think it's sort of the inverse question. They could be both separated in space and time, but they cannot be connected by information transfer because it would have to be going faster than the speed of light. So it works both ways. Yeah. All right. So with that said, what do I want to talk about here? Okay. So this is the energy and momentum stuff. Definitely in our textbook. The stuff that I was talking about, I think, is not. But this is, and again, it's FYI. So we've been talking really about the standard variables we would use in an initial kinematical description of objects, where they are, what time things happen, and then the related idea of velocities. We've yet to mention anything to do with energy and momentum, but you would imagine, if you think about some of the stuff we covered in Newtonian mechanics, of course that's really important. We spend a lot of time talking about energy conservation, momentum conservation, how these are important characteristics. And the same is, of course, true now that we've got a more general theory in the form of special relativity. So we are basically going to define these, and I think there's no attempt to derive this in our textbook either. So it basically just introduces modifications of the expressions we're going to use for energy and momentum. So let's start off with relativistic momentum now. Of course, in Newtonian case, we're used to defining momentum as simply the product of a mass and a velocity, mv. So now, that's not good. Even on here, I seem to have an issue with representing, it's weird. When I looked at it on my computer earlier, this was fine. You see, I brought my laptop down to try and avoid some of the font screw-ups. When I looked at this, it actually said gamma, and so I'm a little puzzled why it's gone back to G. Anyway, this is a gamma factor here. So the definition we need to modify for momentum, to get a relativistically correct expression for momentum, is to throw in a gamma factor. Okay, so momentum now is gamma times mv. There it is broken out for you. As we would expect, and this is always going to be true, I've said on Tuesday a few times that Newtonian mechanics is a special case of special relativity. It's the special case when velocities are relatively low. So what we better expect is that this gives rise to our classical Newtonian answer when we're talking about low speeds. So a simple way to try and check that out might be to take this expression for the gamma factor, 1 over the square root of 1 minus v squared over c squared. How many of you have done Taylor expansions at some point in your life? Okay, good, almost all of you. All right, so I'm going to take that gamma factor as expressed as 1 minus v squared over c squared to the power of minus 1/2. And I'm going to do a sort of initial stage of a Taylor expansion on this. I'm hardly going to go anywhere in that Taylor expansion. But if I do it, then I can represent, of course, mv stays out the front, and now I'm Taylor expanding this term, and the first term is 1. Second term turns out to be half v squared over c squared, and then there are higher order terms. And of course, if v is small relative to c, this term goes to 0, and immediately I retrieve my classical low-speed Newtonian result, okay? So at least a consistency check that is not obviously wrong. So indeed, this seems to be consistent at low speeds. But it turns out this is the relativistic momentum that we need to use. Okay, not a huge deal. It kind of a little bit came out of nowhere, but maybe plausible, maybe not. At least it's consistent with low speed behavior. The energy case turns out to be slightly more interesting. And in fact, the expression